All right, guys, so we're going to get started with lesson 4.2 today. We're going to be talking about reflections. All right, so a reflection is another type of transformation, and a reflection is also a rigid motion or an isometry, as we talked about in the last lesson. Okay, so we're going to start out with some new terminology and notation, and then we'll jump into some problems. So a reflection is a transformation that uses a line like a mirror to reflect an image. The mirror line is called the line of reflection. Okay, so you can see here in this diagram that we have point P and point P prime. Here is my pre-image, here is my image. It flipped over, it reflected over line M. M is called the line of reflection. Okay, you'll also notice, and this is some stuff we're going to talk about down here, but I'll point it out as we're looking at the diagram, that the distance from P to the line of reflection is always going to be the same as the distance from P prime to the line of reflection. And they connected P to P prime to show you that from P to the line of reflection, the tick mark there, is equal to the distance from P prime to the line of reflection. So they connected it again and put a little tick mark to show that the distances are the same. Also, that line that connects P and P prime, the pre-image to its image, that line is always going to be the perpendicular bisector with the line of reflection. Okay, so the line of reflection is going to be perpendicular to the line that connects the pre-image to the image. Okay, and the line of reflection is also going to bisect that line that connects the pre-image to the image. All right. A reflection in a line M maps every point P in the plane to a point P prime, so that for each point, one of the following properties is true. If P is not on M, then M is the perpendicular bisector of P to P prime. All right, or if P is on M, then P is equal to P prime. So this last part, all that means is if you have a point that is on the line of reflection, when you go to reflect it, it's still the same point. So P and P prime are the same point when it's on the line of reflection. All right, a point and its image lie on opposite sides of the line of reflection unless the point is on the line of reflection. Okay. So here it says reflecting a horizontal and vertical line. Graph triangle ABC with vertices A, B, C as given, and its image after reflection described. Okay, so let me make the first grid a little bigger so it's easier for me to graph. All right, so I'm going to be plotting the given points to start. Where am I? Okay, so I have 1, 2, 3. Here's point A. Point B is located at 5, 2. And C is located at 2, 1. All right. I guess I should have, let me write C outside of the triangle instead of inside. Let's see. Okay, there's my triangle. Now you're asked to reflect that in the line x is equal to 3. And that's where you have to kind of go back and remember some algebra 1. X is equal to 3. If I go to where 3 is on the x-axis, x is equal to 3 is a vertical line that goes through 3 on the x-axis. And that's because every point on this line is going to have an x-coordinate of 3. So this is my line of reflection. The easiest way to reflect a figure over a line of reflection is to reflect each point individually first. So C is 1 unit to the left of the line of reflection. So C prime is going to be 1 unit to the right of the line of reflection. A is 2 units to the left of the line of reflection. So A prime is going to be 2 units to the right of the line of reflection. And B is 2 units to the right of the line of reflection. So B prime is going to be 2 units to the left of the line of reflection, right? And that is how simple it is to reflect an image, okay, or a figure over a line of reflection. Now, if you were to connect, just as one quick example, A and A prime, if you were to connect them with a segment, All right, notice that from A to the line of reflection is the same distance as A prime to the line of reflection, and that segment that connects them is perpendicular to the line of reflection. Those are the two properties we spoke about, and that's true for B to B prime and C to C prime. Okay, let's go ahead and try the next one. Make this small again. All right, so we have to start with the same triangle. So I'm going to start with triangle 1, 1, 2, 3, 1, 3. There's A. B is 5, 2. That's B. And C is 2, 1. That is C. Right. This time I'm reflecting over the line y is equal to 1. So I'm going to go to where y is equal to 1, and y is equal to 1 is the horizontal line through 1 on the y-axis, because every point on this line has a y-coordinate of 1. Okay, reflecting B over the line of reflection right now, B is above by 1 unit, so I'm going to go straight below by 1 unit. That's B prime. Prime. A is 1, 2 units above, so I'm going to go 1, 2 units below, and that's A prime. C is on the line of reflection, so C prime is also on the line of reflection. I'm going to connect them, and I have my reflected image. Okay, again, connecting A to A prime or B to B prime. I guess I'll do one more quick example. If I was to connect them, the distance from B to the line of reflection is the same as the distance from B prime to the line of reflection, and that segment that connects them is perpendicular to the line of reflection. Okay? All right. All right, so moving right along, coordinate rules for reflections. If AB is reflected over the x-axis, then the y-coordinate is going to change signs, because when you reflect over, here's your x-axis, if you reflect over the x-axis, it's just the y-coordinate that's changing signs. And if you reflect over the y-axis, your x-coordinate is going to change signs. When you reflect over the y equals x line, which just as a quick visual, if we had a coordinate plane, this would be the y equals x, because every point it goes through, such as 1, 1, right? Or 5, 5, the x is equal to the y. Here I have like -1, -1. -3, -3. So the x and the y are equal to each other. So when you reflect over the line y equals x, the coordinate is just going to flip. And when you reflect over the y equals -x, then the coordinate is going to flip and change signs. And the y equals -x is this line here. Okay, think about some coordinates that are located on that line, like this point here is located at -1, 1. This point here, we'll call that like -4, 4. All right, this point down here, we have a +3, -3. Okay, so you can see they have the same value, the same number, I should say, but different signs. All right. Okay, so here it says reflect in the line y equals -x. We're going to graph FG. Oh yeah, I think it's supposed to be a segment. I should have a segment bar over top of that. That's what I was looking at. I think that's missing. So we're going to graph segment FG with endpoints F -1, 2, G 1, 2, and then its image after reflection in the line y equals -x. Okay, so let me write those coordinates down first. F is -1, 2. G is 1, 2. I'm going to plot them. -1, 2. Here is F. And then G is 1, 2. Here's J. All right. So if we want to reflect over y equals negative x, or you can think of that's the same line as x equals negative y. Think about what that's saying, okay? Your new x is going to equal the opposite of y. Your new y is going to equal the opposite of x. So for f prime and g prime, you're going to flip the coordinates and change their signs, okay? Because your new x is going to be the opposite of y. So the opposite of y is -2. I'll do g first. And then your new y, go up here, your new y is the opposite of x. So the opposite of x is -1. So I flip them and change their signs. So if I flip and change the signs here, it's going to be -2, 1. Okay, so I'll plot those in red. I have -2, 1. That's f prime. And I have -2, -1. That is g prime. I didn't draw my line of reflection. Maybe I should do that so we can talk about it. The line of reflection goes through all of the coordinates where the x and y's are opposites. So points like 1, -1, 2, -2, 3, -3, 4, -4. This is the line of reflection for this problem. And now if you think about connecting g to g prime, like we did in the last few problems, does it appear that g to the line of reflection is the same distance as g prime to the line of reflection? And does it look like the segment that connects them is perpendicular to the line of reflection? Okay, and same thing with f and f prime. They're the same distance away from the line of reflection, and the line that connects them is perpendicular to the line of reflection. Okay, so this is the line y equals -x. All right, let's keep on moving along. Reflection postulate. A reflection is a rigid motion, as I said at the beginning of class, and we saw in the last lesson. A glide reflection, it's exactly what it sounds like. Okay, you glide first, you translate first, then you reflect. So is a transformation involving a translation, a slide, followed by reflection, in which every point P is mapped to a point P double prime because it's moving twice, right? Slide first, that's going to be P prime, and then you're going to reflect it second, that's going to be P double prime. So step one is to first perform the translation to map P onto P prime, then a reflection over whatever line you're told, and that maps P prime onto P double prime. All right, so we're going to practice down here. Let's first graph the triangle that's given. So 3, 2. That's A. 6, 3. Come on. That's B. 7, 1. That's C. All right, here's A, B, C. You're first told to translate. So again, you have A, B, C, which were given as 3, 2, 6, 3, and 7, 1. So we're going to translate first, which when I translate, I have to follow the rule that's given. I'm going to have A prime, B prime, C prime. The rule is to subtract 12 from all the x's and the y's do not change. So 3 minus 12 is going to give you -9, 2. 6 minus 12 is -6, 3. And then 7 minus 12 is going to be -5, 1. So I'll plot those points first. And you could just, of course, come up here and count as well if you didn't want to do the algebra down below. So if I'm subtracting 12, moving 12 units to the left, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So -9, 2 is what we said, and there it is. There's A prime. Then B prime is -6, 3. That's B prime. C prime is negative 5, 1. There's C prime. All right, and we'll connect them to make our triangle. And then finally, we have to perform the reflection. So that's going to leave us with A double prime, B double prime, and C double prime. Now, if you remember from the previous page of the notes today, it said that when you reflect in the x-axis, and just think about this, if you have a point above the x-axis and you reflect it below the x-axis, what coordinate is changing signs? It's the y-coordinate that's changing signs. So all your x's are going to stay the same, but all your y-coordinates are going to change signs. So negative 2, negative 3, negative 3, and then negative 1. And again, you could just come over here reflecting over the x-axis on 1 unit above. So I need to go 1 unit below. C double prime, excuse me, is there. For B, right now I'm 1, 2, 3 units above, so I need to be 1, 2, 3 units below, which I said should have a coordinate of negative 3, which it does. So here's B double prime. And then A prime is 2 units above, so A double prime is going to be 2 units below. And there is your glide reflection, your translation followed by reflection. Right. Okay. Let's see what else we have going on. All right, it says a figure in the plane has a line of symmetry when the figure can be mapped onto itself by a reflection in a line. This line of reflection is called a line of symmetry, such that line M at the right. Okay, so here you see a butterfly. Line M is your line of symmetry, also a line of reflection. A figure can have more than one line of symmetry. Okay, so this is good practice to determine the number of lines of symmetry that each figure has. Okay, so how many lines of symmetry do you think the first figure has? There are 2. We can draw them. We have a vertical line of symmetry, and we have a horizontal line of symmetry. What about the next figure? There are 5. This is called a regular polygon. It's a regular pentagon. A regular pentagon is a pentagon that has 5 sides that are all equal in length and 5 angles that are all equal in length. All of our regular polygons have the same numbers of line of symmetry as number of sides or number of vertices. So here is 1 line of reflection or line of symmetry. Here's another one. The third. Oop, that was a little off. The 4th line. And finally, the 5th line. All right. But the next one, how many lines of symmetry do you think they have, the triangle has? Only 1. Okay, this is not a regular triangle. It's not an equilateral or equiangular triangle. Just 1 line of symmetry. Okay. All right, that I think is going to be just, let me take a quick look. Yep, that's going to be it for this lesson. So let me just go back to the screen. All right, guys, so that is it for lesson 4.2. I'll see you back here for the next lesson. Bye.